Last two lectures we have narrated few coupled oscillator problem and solved them using the technique of small oscillation that we have developed. In this class we shall address one more point of small oscillation, that is, sometimes instead of describing the system, one may be supplied with the Lagrangian, and then the task is to identify T and P matrices and solve for the smaller eigenvalue, eigenvector problem, etc. We assume that the system for which of which the Lagrangian will be supplied is a conservative system, so that the potential energy does not have any dependence on velocity. So the Lagrangian, the velocity dependent part of the Lagrangian is taken within the kinetic energy part, and the position dependent parts are taken within the potential. As for example, so our task is to identification of T and B matrices when a Lagrangian is supplied, and then to solve for eigenfrequencies and eigenvectors, etc. Maybe normal coordinates like this. So this is our task. We start our discussion with a simple Lagrangian that we consider L to be half mx dot square y dot square minus half m omega square x square plus y square plus alpha xy. Obviously this is the kinetic energy part, so we identify this part as the kinetic energy, and this part is the potential energy, of which this part is the restoring force that acts on an two-dimensional isotropic oscillator. So this is the potential V corresponding to the restoring force for a 2D isotropic oscillator, 2D isotropic harmonic oscillator. Isotropic because the spring constant is same for x and y, and this is the coupling term, coupling potential. Coupling potential, as we have encountered in earlier case, the potential is x minus y whole square. So this can be written as x square plus y square minus twice xy. So this part is included over here, this part is included over here, and this is the part left which is taken within this coupling term. So the T matrix is obviously is M1001, and the B matrix we have the diagonal term is m omega square. This is m omega square, and for this it is minus alpha, because this should be minus T minus B. So this is the B matrix. So now we can go for the solution of eigenvalues and eigenvectors adopting the usual sense. So the T matrix is, for this problem, T matrix is diagonal M1001, and B matrix is M omega square minus alpha M omega square. Now for this, as a second example, we consider a Lagrangian L is equal to half mx dot square y dot square plus beta x dot y dot minus half m omega square x square y square. There is no coupling in potential term. This term arises because of the fact that there is a interaction of this form. This is called inertial coupling. This is known as there will be a term in this form, and the force, corresponding force, is of the form the x double dot minus y double dot square. So this is called inertial coupling. We shall come to this part in the second half of today's lecture. So this part is T. So T matrix for this is M, the diagonal elements, and this is beta, and the B matrix is, it is diagonal M omega square 1 0 0 1. So this is known as the stiffness coupled oscillator, and this is known as inertia coupled oscillator. We shall come to the nomenclature and example afterwards. And there is a third example. Here this oscillator is both inertia coupled and stiffness coupled. This is the kinetic energy part, so T operator is M diagonal element. This is beta is the off diagonal elements, and the B matrix is M omega square as the diagonal element, and this is minus alpha. So this oscillator is simultaneously stiffness coupled as well as inertia coupled. We shall now describe the types of coupling, and we will confine our discussion to two coupled oscillator system and the types of coupling. We shall start our discussion in Newtonian form, and then we shall describe the Lagrangian form. So simple, two coupled oscillators, coupled oscillator system. Types of coupling. First thing that I want to mention, so we consider 2-point masses. System is comprising of M1 with coordinates x1 and M2 with coordinates x2. So the oscillator system comprises of 2-point masses M1, M2, which are moving in 1D along x-axis, and the displacement of the point m1 of the oscillator m1 from its equilibrium position is denoted by x1, and that of m2 is denoted by x2. Since we are considering oscillators, so they must be acted upon restoring force. Restoring forces is minus k1 x1 and minus k2 x2. So uncoupled oscillator, for uncoupled oscillator, the equation of motion would be m1 x1 double dot is equal to minus k1 x1 and m2 x2 double dot is equal to minus k2 x2. If we like to get the Lagrangian of this system, the Lagrangian of this system will be half m1 x1 dot square plus half m2 x2 dot square, and this corresponds to potential energy half k1 x1 square minus half k2 x2 square. Now coming to the matrices, T matrix, we call it T0 matrix. It is m1 0 0 m2, and the V matrix, which is V0, because this is the uncoupled system, so this is K1 0 0 K2. So since there is no coupling, both T and V matrices are diagonal ones. Now we come to stiffness coupled oscillator. Stiffness coupled oscillators. It is the type of oscillator that we have discussed earlier. This means that the mass point m1 was attached by a spring of spring constant k1, and the mass point 2 is attached by another spring of spring constant k2. This is the uncoupled oscillator. Stiffness coupled means these two oscillators are now coupled by another oscillator of spring constant kappa, so that the force that acts on one, so if we consider equation of motion m1 x1 double dot, this is the inertial force acting on it, k1 x1 due to the spring, kappa x1 minus x2, and for the particle 2 it is m2 x2 double dot is equal to minus k2 x2 minus kappa x2 minus x1. Actually, this is called the coupling spring. This is the coupling spring. If we rewrite this equation, we get m1 x1 double dot plus k1 plus kappa x1 is equal to kappa x2, and for this we have m2 x2 double dot plus k2 plus kappa x2 is equal to kappa x1. This is the stiffness coupled oscillator. This is the Newtonian form of equation. This is also the Newtonian form of equation. If we like to write this, then it should be plus and is equal to 0. The Lagrangian for stiffness coupled oscillator is the kinetic energy, in the kinetic energy there is no coupling. x2 dot minus half k1 x1 square minus half k2 x2 square minus half kappa x1 minus x2 square. So the spring, so to say, the oscillator exchange energy among themselves via the coupling spring. So to write the T matrix is, T matrix for stiffness coupled oscillator is same as the uncoupled oscillator, and this is M1 0 0 M1, and the B matrix is changed. B matrix, it is K1 plus kappa, this is K2 plus kappa, this is minus kappa minus kappa. This is the stiffness coupled oscillator, B matrix for stiffness coupled oscillator. So to say, the example that we have considered till now are the stiffness coupled cases. There are other types of coupling, the inertia coupling, inertia coupled oscillators, in which case the oscillator 1 is acted upon by this force. This is a customary force. This restoring force must be customary for this particle to be an oscillator. So the it is the for particle 1 it has, this is the inertial force, this is its restoring force, minus it is acted upon by a force which is x1 double dot minus x2 double dot. That is the force, the force of coupling dependent on relative acceleration. In this case, in the case of stiffness coupled oscillator, the force of coupling was found to be dependent on relative displacements, and so and for the particle 2 it would be m2 x2 double dot minus k2 x2 minus mu x2 double dot x1 double dot. So that if we rewrite the equation, we have m1 plus mu x1 double dot plus m2 plus mu x2, sorry, then this part k1 x1 is equal to mu x2 double dot, and for the particle 2 it is m2 plus mu x2 double dot plus k2 x2 plus mu x1 double dot. This is known as inertially coupled oscillators. Such oscillators arises in mutually coupled LCR circuit. The example of this type of oscillator is mutually coupled LCR circuits are the examples of such a system. Now, the T matrix will be, this is the inertia coupled system. The T matrix will be m1 plus mu, and this diagonal element is m2 plus mu, and this is minus mu, and the B matrix is B0. There is another type of coupling present. This is known as resistive coupling. If the oscillator was allowed to move in a dissipative medium, that is when there is air resistance, hysteresis, etc. are present, then the oscillator experiences another force which is dependent on its velocities. So the for resistance, when the dissipative forces are present, then we will have another term to be added to it. This is minus b1 x1 dot, and here we have to add minus b2 x2 dot. This is the resistive force. Furthermore, one thing may happen, such as consider a planet. When a planet moves, it drags its atmosphere around, surrounding it together with it. If we have another part of the oscillator, say its satellite, which is moving around very close to it, then both these two, planet and its satellite, will experience a force which will depend on the relative velocity. Then we will have a resistance coupling system, in which case the force will be x1 dot minus x2 dot. This is known as resistive coupling. So if we add the resistance coupling with it, so the resistance coupling, then the equation of motion for the first particle will be m1 x1 double dot minus k1 x1 minus b1 x1 dot minus beta x1 dot x2 dot, and for the particle 2 it will be m2 x2 double dot minus k2 x2 minus b2 x2 dot minus beta x2 dot minus x1 dot. So this equation becomes m1 x1 double dot plus b1 plus beta x1 dot plus k1 x1 is equal to beta x2 dot, and for the particle 2 it is m2 x2 double dot plus b2 plus beta x2 dot plus k2 x2 is equal to beta x1 dot. But the presence of this damping term makes the system non-conservative. So such oscillators cannot be fitted within the theory of small oscillation that we have developed for conservative system. Rather, we can treat it in the Lagrangian formalism by introducing the Rayleigh dissipation function. Let me outline the Rayleigh dissipation function for such a system. The Lagrangian of the system is half m1 x1 dot square plus half m2 x2 dot square minus half k1 x1 square minus half k2 x2 square, and the Rayleigh dissipation function is half b1 plus beta x1 dot plus half b2 plus beta x2 dot square. And recall that the Euler-Lagrange equation involving Rayleigh dissipation function is del ddt of del L del xi dot, here we call this as the resistance coupling, so this is R, minus del R del xi plus del R del xi dot is equal to 0. This leads to, if we take the L and R of this form, which leads to this is. Now, since this resistance coupling cannot be taken into consideration within the theory of small oscillation, we are, for the time being, not considering the coupling via velocity, relative velocity. So in one words, in stiffness coupling, the exchange of energy takes place by a force which depends on the relative separation. In resistance coupling, the force is dependent on the relative velocity, and in the inertial coupling, the force is dependent on relative acceleration. So finally, we consider stiffness inertia coupled system. So we consider two oscillators which are connected to each other via stiffness coupling and as well as via inertia coupling. So the equation of motion for the first particle is m1 x1 double dot. This is its restoring force. The coupling through stiffness coupling is this, and coupling via inertia coupling is, and for the particle 2 it is m2 x2 double dot minus k2 x2 minus kappa x2 minus x1 minus mu x2 double dot minus x1 double dot. This equation can be written as m1 plus mu x1 double dot plus k1 plus kappa x1. Then on the right hand side we have kappa x2 plus mu x2 double dot. This is the coupling force. And for the second one, it is m2 plus mu x2 double dot plus k2 plus kappa x2 is equal to kappa x1 mu x1 double dot. The Lagrangian for such a system, the Lagrangian is minus half k1 x1 square minus half k2 x2 square minus half kappa x1 minus x2 square. So this can be written as half m1 plus mu x1 dot square plus half m2 plus mu x2 dot square minus mu x1 dot x2 dot minus half k1 plus kappa x1 square minus half k2 plus kappa x2 square minus also plus kappa x1 x2. Now you recall that the example that we have considered, we have taken such term, coupling term and such coupling term, and then we remark that this is an inertial coupling and this is this is stiffness coupling and this is inertia coupling. So if we want to identify the matrix, since it is inertia coupled, so T matrix is not diagonal, and at the same time, as it is stiffness coupled as well, V matrix is not diagonal too. So this is the T and identification of T and V matrices for different types of coupled oscillators. So we have outlined the different types of coupling that may take place in the case of coupled oscillator. The examples that we have considered till now are the oscillators which are coupled each other via stiffness coupling. In the next class we shall consider an example where the oscillators are coupled via inertia coupling, that is the double pendulum problem.